All right, let's jump right in. You ever stop and think about what powers the really big stuff? I'm talking massive industrial machines. Well, a lot of the time, the answer is a circuit just like this one, the three-phase bridge rectifier. Seriously, this thing is an absolute workhorse in power electronics. So today, we're going to tear it down and see exactly how it takes high-power AC and turns it into the DC that, makes our world go round. So here's our game plan for this explainer. We'll start by getting familiar with the circuit itself. Then, we're going to dive into the math behind it all. After that, we'll walk through a real-world example, see if our numbers hold up in a simulation, and then we'll wrap up by comparing it to its single-phase cousin to see why this one is such a big deal. Okay, first things first, the three-phase bridge rectifier itself. We've got to understand what we're looking at, right? Let's get a handle on the basic circuit and how it operates before we even think about touching the math. And here it is, the circuit in all its glory. So what are we looking at? Over on the left, that's our three-phase AC supply coming in. In the middle, you see those 6 diodes? That's the bridge. That's where all the magic of rectification happens. And then on the right, that's our load. And notice, it's not just a simple resistor. We've got a resistor, an inductor, and a DC voltage source. This is a super common setup, by the way. Think of it as modeling something like a big DC motor drive. Now, the whole show is driven by the line-to-line voltage. That's the voltage between any two of those 3 input phases. And this equation you see here, it's really important. Why? Because with 6 diodes in that bridge, the circuit is constantly switching which pair of diodes is active. It happens every 60 degrees of the AC cycle. So this formula is basically our snapshot. It tells us exactly what piece of the sine wave is actually doing the work at any specific time. All right, we've got the voltage sorted. So the next logical question is, what about the current? Let's get into analyzing the output current. This is where we're going to roll up our sleeves and derive the math that really explains what's happening in that load. Okay, I know this differential equation looks a little intense, but don't let it scare you. All this is, really, is Kirchhoff's voltage law dressed up for a party. It's just saying that the voltage coming out of the rectifier has to go somewhere. It gets spent, you could say, across the different parts of our load. A piece of it drops across the inductor, another piece across the resistor, and the rest has to fight against that DC voltage source. That's it. Now, when you solve that equation, you find out the solution has 2 distinct personalities. First, you've got the steady-state response. That's the part that's being forced by the AC sine wave from the input. But then you've also got this transient response, kind of like the circuit's natural reaction, an exponential decay caused by the resistor and inductor. The total current we see is just these 2 parts added together. So how do we find the exact solution for our specific circuit? Well, we need to use a couple of key conditions. We know what the current is at the start of a cycle. And here's the really clever part. Because this thing is running in a steady state, we know that the current at the end of one of those 60-degree windows has to be exactly the same as the current at the start of the next one. It's a repeating pattern. And once you realize that, you can use these facts to nail down all the unknown constants in the equation. And voila! After you combine all those conditions and solve it all out, you get this. This is the big one. This is the full expression for that instantaneous output current. I know, it looks like a beast, but trust me, every single term in there means something. It's telling a story about the circuit's behavior, accounting for everything from the input voltage to the load's R and L values. This is it, our complete mathematical model. But hang on a second. This whole thing we just did, it's based on one huge assumption, that the current never actually stops flowing. We're assuming the inductor is big enough to keep things moving. But what happens if it isn't? What if the inductance is low and the current actually drops all the way to 0 in between pulses? Well, that's a whole different ballgame. That's called discontinuous conduction mode, and it completely changes how the rectifier behaves. So how do we know which mode we're in? This chart tells us. It's basically a map. On the vertical axis, you've got the ratio of your DC source voltage to your AC input voltage. And on the bottom, the horizontal axis, that's the load angle, which is just a fancy way of saying how inductive is my load. The takeaway is super simple. Stay above the line and your current is continuous. If your operating point falls below that line, your current is going to become discontinuous. It's that clear cut. Okay, enough theory for a minute. Theory is great, but let's see how this stuff actually works in a practical example. It's time to plug in some real numbers and see what happens. All right, here's our setup. We've got a pretty standard industrial supply. 208 volts line to line, running at 60 hertz. Our load has a resistance of 2.5 ohms and an inductance of 1.5 millihenries. And that 10-volt DC source, again, you can just picture that as the back EMF from a DC motor that's already spinning. So let's take these numbers and pop them into that big equation we worked so hard to derive. And check out what the math spits out. We get an average DC current of 105.77 amps and an RMS current just a bit higher at 108.31. But here's the number I want you to really notice. The power factor is 0.92 lagging. For an industrial rectifier, that is fantastic. It means this circuit is using power from the grid incredibly efficiently. We're not wasting a lot of reactive power, which is great for the electricity bill and for keeping the power lines clean. Okay, so our math gave us some pretty nice-looking numbers. But here's the thing about engineering. You never just trust the math on its own. You always verify. So let's fire up a simulation and see how well our model holds up to a virtual reality check. Okay, remember this number. Our paper and pencil calculation said the average output current should be 105.77 amps. Let's lock that in. Now, what does the simulation say? And would you look at that, the PSpice simulation ran the numbers and it calculated an average current of 104.89 amps. Let's think about that. We calculated 105.77. The simulation got 104.89. That is an incredibly close match. We're talking less than a 1% difference. This is exactly what we want to see. It tells us our mathematical model is rock solid. So we've gone really deep into the weeds on this one circuit. Now it's time to zoom out and look at the bigger picture. Why go through all this trouble with a three-phase rectifier when single-phase rectifiers exist and are way simpler? Let's compare them. This table really says it all, doesn't it? It boils down to one word: power. A three-phase rectifier can handle insane amounts of power. We're talking megawatts. Plus, the DC it puts out is much smoother with way less ripple. And we already saw it has a great power factor. Single phase is great, for smaller applications up to maybe 100 kilowatts. But when you get into serious heavy-duty industrial stuff, three-phase is pretty much the only game in town. So let's wrap this up with the key takeaways. What are the big ideas to remember? Number one, that inductor in the load is absolutely critical. It's the hero that smooths out the current and keeps it flowing continuously. Number two, if you make that inductor really big, the input current starts to look less like a sine wave and more like a quasi-square wave, which is interesting. And finally, and this is the big one, these rectifiers are the undisputed champions of high-power industrial applications, anything from 50 kilowatts clear up into the megawatt range. And that brings us to a final question to chew on. We've spent all this time on the how and the what, but what about the where and the why? We talked a lot about motor drives, but where else do you think this kind of high-power, smooth DC is absolutely essential? Think about it. What about huge electrochemical plants doing electrolysis, or high-powered welding, or even the charging infrastructure for fleets of electric vehicles? The applications are everywhere, and they're all powered by circuits just like the one we analyzed today.